Hello. In this video, we're going to take a look at a linear data set and make use of our calculator to do some analysis on that. And a couple of the maneuvers I'm going to show you on your calculator are useful in many different skills, not just places you'll encounter linear data. So this is a problem where I'll show you how to graph ordered pairs on your calculator, and in this case, you'll see the ordered pairs have a linear nature, which will dictate what type of math we will apply to answer the questions here that are being asked. Okay, so let's take a look. It says Leighton measures the voltage across different numbers of batteries end to end. He records his data in the following table. Then we see we have, for any given number of batteries, 1 through 8, certain voltage measurements that he took with the needed measuring device to measure the voltage when he lined up this many batteries. Okay? So the questions here say let X represent the number of batteries and Y represent the voltage. Find the slope of the line approximating these data. Be sure to include the units with your answer. Okay, we're also going to try and look at this from the standpoint of dependent and independent variable like we talked about in class. B, it says which points did you use in Y and what is the real world meaning of this slope? And C, does it make sense that the y-intercept of this line is 0? Explain why or why not. So let's continue on with our calculator, and what we'll do first is we'll plot this data set. So you need to know how to plot the ordered pairs here. So this routine becomes very important. So I'm going to do stat, okay, and then I'm going to hit edit, and you see it takes us to L1, L2, and L3. These are lists. In L1, I'm going to enter the independent variable, which is X, and Y, which is the dependent variable, into L2. So let's talk about this, okay? So we talked about in class the strategies is to ask yourself the following question, and from two different perspectives, and see which one makes more sense. Okay, and you can say, well, how many batteries do you have in the system? Or can you say, well, it depends on how many volts are present. It's one way to look at it, but there's another way to look at it and say, well, how many volts are present in the system? You say, well, it depends on how many batteries you have in it. I think the second one makes more sense when you say it, so it would mean that the voltage depends on the number of batteries. So batteries is the independent variable, but voltage is depending on that variable. So we're going to say here that the batteries is X and the volts is Y, and the batteries is the independent variable and the volts is the dependent variable. So thinking along these lines and forcing yourself to ask those questions and investigate that idea is so important in many of the real life applications we do in math, and it's continually important in topics in physics, which many of you will find yourself in. Okay, so I'll enter here and go 1, enter, 2, enter, 3, enter, 4, enter, 5, enter, 6, enter, 7, enter, 8, enter. And those are my values for the independent variable. The corresponding values for the dependent variable will be at 1 battery. We measure it's 1.43 volts. Then for 2, it's 2.94, followed by 4.32, 5.88, 7.39, 8.82, 10.27, excuse me, a little typo there, 10.27, and 11.7. Okay? So, well, why am I graphing this data set at all, or why am I doing this? I want to be able to look at the data and get a general idea of what's going on with it and take an overview. So I'm going to continue and make a graph now by doing the following. I'm going to go to second y equals, which if you read above it, it says stat plot, which means you're going to take your stat information and plot it. You have 3 options to do plots here. It says plot 1. We'll modify that by hitting enter. It's currently off, so by hitting enter, you'll turn it on, now that on has a black background. Down arrow, and you notice the first one is a bunch of dots. That's a scatter plot. So I'll hit enter for that. Now if you see by default here, it already says L1 and L2 for X list and Y list, which is appropriate. Okay, that's where I put those X and Y values. So now I'll hit graph, and you see that I kind of see the data. And a good little trick here is there's a zoom feature called zoom stat, which is number 9. And what it does is it looks at the data that's in your lists that you entered using the stat button, and it focuses just on those. Well, if you see here, this data is decently linear. It's not perfectly linear, okay? So it has a linear tendency, but it's not a perfect line. So now as we go to address the first question, where it says, find the slope of the line approximating these data, be sure to include the units with your answer. Well, if I kind of estimated a line, I guess I could take the first and last point in this case, because it seems like it would be sort of drawing a line between them somewhat that sort of approximate the tendency of the rest of the points. So I will do that. I'm now going to find the slope between this point and that point. Okay? So that is going to give me, by the formula we saw in class, we have m equals y2 minus y1 over x2 minus x1, which is going to give me y2, which is 11.7, minus y1, which is 1.43, over x2, which is 8, minus x1, which is 1. And that is going to give us, just by going on my calculator, by hitting the second quit, 11.7 minus 1.43 gives me 10.27. And then 8 minus 1 is 7. Now you have to simplify this because this is a decimal in a fraction. 10.27 divided by 7 is going to give me 1.47, I'll call it approximately. Okay? So 1.47, where it says use a unit. To do the unit, all I need to do is reflect on the fact that I have y on top and x on bottom in this fraction. So I will take the y word and put it on top, which is volts per. And then now I'll go and get the x word, which is on bottom, and write battery. So it is 1.47 volts per battery. I'll just abbreviate with BAT. So now it says which points did I use and why? Well, I used the first and the last. Okay, now that is no hard and true recipe for doing all these problems. But if you look at the data, I notice that if I connected the first point to the last point, it would draw a line that approximates the rest of the data. Okay? So that is why. Because it approximates a line through most of the other data. And this is true because if you notice, if I take a screenshot of this, okay, and let me just for a second go on to my next page, and I will paste it here, okay? If you notice, if I blow it up, just simply connecting the first dot to the last dot, okay, if I just adjust that so it's through the middle, you tend to see, well, that's a decently good model. So I probably could have used some other points, okay? If you notice, if I would use the first and second, though, if I get through the second one that's in the middle and through the first one through the middle, I think that's a little more off than where I was by making that approximation. Okay, so again, when we deal with estimations, you have to accept the fact that they're going to be off a little bit. So, um, you have to kind of deal with the hand you're dealt to some extent, and realize that you're estimating. Okay, so what does it say here? It says, what's the real meaning of your slope? Well, it says I have a slope of 1.47 volts per battery. And because it's positive, it means the slope is increasing. And really, it's just what I'm saying is, I'll verbalize this out. Okay, I'm going to make a little space on the next slide to answer this question. What's the real meaning of the slope? And that is that the voltage increases about 1.4. Again, we estimated that it was 1.47 volts for every one battery added to the system. Okay? Now, the one thing you want to see about the slope is that it is speaking about 2 units. Okay? It is talking about the change in the first unit, or the independent variable, for every change of the change of 1.47 volts, which is the dependent variable, for every change in one independent variable, which was batteries here. Okay? It depends on how many batteries you add. For every one battery you add, you're going to get a change of about 1.47 volts. Okay? So, does it make sense that the y-intercept of this line is 0? Explain why or why not. Well, it's interesting. It would make sense that it is, okay? It would make sense that it is because I'd say yes, because at the y-intercept implies that x equals 0, okay? And 0 batteries should yield 0 volts. Okay? However, in this case, so I'm just going to leave that blank for a second because I got to take you through what I see here. Okay? In this case, it actually might not really be true. Okay? So there's kind of like a little bit of 2 sides to this story. The first side is this. If you don't have any batteries, how could you have any volts present? So I would think an electrical engineer could confirm that. Okay? But the one thing you notice here by the line and the slope, because it's an estimation, the estimation here isn't totally useful. Because if you notice right here, okay, we talk about there's a piece in this chart that's actually missing. Okay? And I'll put it in here for a second. If you had 0 batteries, but use the idea of 1.47 volts of change, well, if you notice, at 1 battery, you're at 1.43. And if you go backwards 1 battery, you should go backwards 1.47 volts. Which in this case, if I took 1.43 and subtracted 1.47, I actually get 0.4. Okay? Which you notice is about 0, but it's not exactly 0. So we say, however, in this case, because we estimated using a line that connected two points to model the data, and this is the important part, to model, which I guess is sort of a little bit an estimate in this case because it wasn't perfectly linear, the data, the line did not perfectly intersect the y-axis at 0. So I guess there's 2 points to this story that you can make, the purple and the red here. Okay, let me try and zoom on this for a second. Okay, so if you notice, well, it says, does it make sense the y-intercept of this line is 0? Explain why or why not. Well, yes, you would expect it to be 0 because the y-intercept implies that 0 batteries should yield 0 volts, just from what you would expect. But however, in this case, because we estimated using a line that connected 2 points to model or estimate the data, which was not perfectly linear, the line did not perfectly intersect the y-axis. So there's a lot that goes on in this problem here. Let's try to review that. One is I took the data set and actually made a graph of it. And I saw that the graph yielded somewhat of a linear data set. Well, that allows me, once I realize that it's linear, to use the notion of this slope formula for a line. Okay? Because if it behaves like a line, if it's not perfectly like a line, if it's close, it's not a bad tool. You just then have to keep in mind that you're estimating. Okay? Which points did you use and why? That's going to vary from problem to problem, and that's even an opinion. So maybe some opinions are better than others, and you would have to back that up. But the one thing you notice is I thought it was reasonable to say, well, if I connected the first point with the last point, I would get a decently good model for the rest of the data as well. So that was a pretty good deal. Okay? Excuse me. So then if you notice also too, what's the real meaning of the slope? I can't emphasize this enough. Every slope is a number, but there are two quantities being related. Every time we talk about analyzing a slope or explaining it, you can say the slope number and then talk about the y unit per one x unit. So in case you've got the slope number is 1.47 and the y unit is volts, per one x unit is batteries. So we say the slope is 1.47 volts per battery, and it talks about the relationship of change between those as they simultaneously change. So I hope this was a help. I'm sorry I ran out of time in class, and I hope that this helps you address a problem similar you're going to see in your homework. Enjoy.